Hello friends, welcome again to my course. Electric vehicles, which have the advantage of being pollution-free, low in noise emissions, and very fuel efficient, have become the trend in the automotive industry. The drive system of electric vehicles is of great theoretical importance and practical value for the study of the drive motor and its control system. With its simple structure, small size, low weight, low inertia, and high power density, the PMSM is very well suited for the limited space of electric vehicles. Furthermore, the PMSM is also very well suited for starting and acceleration requirements due to its high efficiency, high power factor, high torque to inertia ratio, high overload capacity, and high output torque, especially at low speeds. As a result, various factors have led to PMSM becoming one of the most important decisions for the drive system of electric vehicles. After designing PI control systems for drives, this video discusses the implementation of cascaded PI control systems. Since control systems for electric drives are configured as cascaded control systems, with PI controllers for internal and external control loops, there may be differences in the implementation algorithms. In addition, operational limits are imposed when implementing the control system. For example, operational limits on voltages and currents are necessary to protect electronic equipment under high load and transient conditions. With these limits imposed, if a PI controller is used in the control system, anti-windup mechanisms are required to ensure a satisfactory closed-loop performance. The current control signals are D-axis and Q-axis voltages, VD and VQ. Due to the operation of the inverter, the DQ-axis voltages for electric drives are limited by the PWM and DC voltage. Assume that the DC link voltage is VDC. Then, the amplitude of the space vector voltage signal is limited when using PWM with harmonic injection or space vector PWM. As we saw in this video, this limit leads to limitations in the amplitudes of the D and Q axis voltages. So we should determine the maximum and minimum values of VD and VQ in real time by scaling the values of actual VD and VQ proportionally. Assume that at the sampling instant Ti, the two current control loops have these computed control signals, and that the voltage constraint equation is violated. If the voltage constraint violation occurs, then the solution is to find VD new and VQ new of this equation. So we should maintain the same ratio while satisfying this constraint. This figure illustrates a possible solution that will satisfy the constraint while maintaining the same voltage ratio. The limits of the D-axis and Q-axis voltages are varying with respect to time depending on the computed control signals. The first step in the implementation process of controllers is to discretize the continuous time controllers. In the general case, we assume that the feedback error is E and the feed-forward function is F. Then, with Kc, the proportional gain, and tau, the integral time constant, the control signal U from a PI controller is defined as the two most important points when implementing an anti-windup mechanism in controllers are 1. A stable control structure. 2. Ensuring that the actual control signal matches the calculated control signal. The actual control signal must satisfy this constraint in order to stop the integration when the actual control signal reaches the limit. We impose the limits on the actual control signal. The manipulated variable in the speed loop system is the reference current signal to the current loop system, so the constraints are imposed on the manipulated variable IQ star. These limitations provide overcurrent protection in the event of an overload or a high transient response for fast machine startup and shutdown. The constraints are simply imposed as where IQ max is the maximum current allowed. When implementing the PMSM current control, we have two options for configuring the control system. The first is to use a proportional controller for the coaxial current control system. The second is to use a PI controller for the same loop. The PI controller is required for the D-axis current control system because it has an integral term. It eliminates the steady-state error in the closed loop, and there is no external loop system for the D-axis current control system. We have already covered and developed all of this in detail during the last videos. What we still add today is to integrate this embedded controller into the simulation for the speed control of the synchronous machine. In the simulation today, we will only look at the controller blocks. Everything else we have already looked at several times. To implement the real-time PI control algorithm, we produce an embedded MATLAB function that can be used in a Simulink simulation.